Hey everybody, welcome back. What is this, part 4? Part 4, I think. And we finally got the capacitor boards in. There's nothing special about them. They're just, you could probably just do this on a piece of perf board, but a little neater to do it this way. So I'm going to, just to make easier access, I'm going to pull this amplifier module back out because it's just as simple as unplugging these 4 connectors and 4 screws. And then we're going to remove these main filter caps and replace it with the boards. So once I get into this a little bit, get it taken apart, we'll be back. Okay, we have the old capacitors removed, and we have these 4 standoffs put in there. The star ground bus just stays in place where it was. These wires from these connectors are just going to go up through the holes, and they're going to connect to the board. And you can see there's 1, 2, 3, 4 connections. And then we have our grounds, which are going to go down onto the 2 ground buses. And then this just attaches right here. And we have to, first of all, install the capacitors, and then we can bring the wires up through and solder them on the back of the board. So let me get the caps put in, and we'll get this thing fitted. Okay, the board is fitted on there. One thing that you have to remember about these capacitors is these 2 and these 2 are going to have the negative B- voltage on them. So if you touch this case with respect to ground, that would be the 53 volts. Now, it probably wouldn't shock you, but it's probably not safe to have that up there. If something falls across here and here, it would make a short. So what I did was I took some of this really thick shipping tape and just cut little discs out and put them on there for now. I may try to find some round stickers, something a little more durable to put on there and cover them up later. But for right now, I think that'll be fine. That's just enough. I put 2 layers of it on top of one another, so it's really thick, and yet it's just glued on, so if this thing needs to vent and pop open, it'll just pull the tape right off. But that's just a little bit of safety in there for just a little bit extra caution. You know, if you ever do something like this, you don't have to do that if you don't want, but it's just an extra level of safety. Okay, I have the dim bulb tester turned on. Let me plug this in. And I'm going to power it up, and the first thing we're going to see is if our lights turn off, or our dim bulb dims down. And it does. It's real dim, so that's good. It charged up. Oh, and the protect relay came in. So that's good. So now let's go through and measure our voltages. Here's the first negative for the one side, and it's, again, we're going through the dim bulb, so our 53 volts is going to be low. It's negative 40. Then our positive line is right down here, and there's, I'm sorry, the other negative line is there. Okay, and then our positive line is over here, and it is, and then we already tested the negative, so here's the other positive side, and it's good. So all 4 of the power leads are working, and they're fine. Now if you zoom in a little bit, you can just kind of see this black wire here. There's one here, and there's one over here, and they connect to this star ground, which we just kind of left in place. So all the grounding is exactly the same. All right, let me turn this off. And before I plug this in, now these caps are really, really charged up. So what we're going to do is we're going to discharge them. And I can use my stinger cable, and you've seen that before. But we'll use another simple discharge tool. And it's just a light bulb in a socket and just 2 meter leads. So if you don't want to make one of those stinger cables, and you've seen that in a lot of my other videos, we can use one of these, and I'll show you how it works. It's pretty cool. so you can visually see the capacitor discharge. So here's the negative, go on the positive. That side's down, that's good. That one had a little bit on it, did you see it? That one was down. And this last one. And that one was discharged. Okay. All right. So those all seem to be discharged. Yep. Okay, now we can plug these in, and we should see the amplifier come up this next time. So let's plug this in here. Plug this one in here. Oh boy, that's sharp there on that end. That's pointy. There. Okay. All connected, and then I'll clean up some of these wires along here later on after we do our tests. And let's see if it comes up. And again, we're going to just check with the dim bulb. If something draws heavy current or shorts out, I'm only using the 40-watt bulb right now, so it won't allow very much current. That bulb will light up pretty bright. Okay, turning on. And it is drawing a little bit more current now. And it looks like we're getting 212 milliamps, and we're not getting the protect light coming in because there's just not enough current to let the voltage come up far enough so that we can get the protect relay to come in. Okay, let's go to the next bulb up, and let's turn it on again, and we should hear the protect relay, and I will move the microphone over close to the board so we can hear it. Here we go. There it went. Did you hear it? It came in. Okay, and you can see how incredibly dim that bulb is there. So it's very, very low current. So I believe that everything is working properly. So now we can connect this up and see if we can get it to pass a signal and try to get some sound out of it. Okay, the unit is powered up, and so far no problems. And of course the air conditioning, everything in the house is running, so there's all kinds of background noise, but the bulb is on very, very dim, and I'm going to switch to direct here in a minute. But the first thing we're going to do is turn up the volume a little bit, listen to it at low volumes with the current limiter on it, and then we're going to switch to direct and turn the volume up a little louder. So starting a song now, turning the volume up. You can see. Okay, it's working. Okay, let's switch to direct full power. Heard the mid-range come in really nice when the power came up. Okay, now let's turn it up. The loudness switch was on. Not a very good song. Let's see if I can find something else here. I don't know what all this stuff is. Arabian Sand. Not too bad. happy. Sounds good. It's working. Of course, we haven't done any testing on this or anything, but everything is good so far. Feels nice and cool. Let's turn the power off. Turn it around here. I just want to make sure none of these capacitors are warming up on us or anything like that. Nope. They're all ice cold. So there's no problems. Everything looks good. Well, thinking about this, I know I'm probably going to get a whole bunch of questions about the capacitors and why I did what I did. So hopefully I'll head off as much of that as I can here. The original caps that were used were these dual capacitor modules. So if you look inside here, there is a 6800 microfarad capacitor here and a 6800 microfarad capacitor here, and they're wired in series, and then the center of them comes out. So you can see you have 3 different leads that match these leads, but this is internally there are 2 capacitors. Now if we look down here, I drew a little diagram of a few things to answer some questions that I know I'm going to get on this. So let me get the camera lined up. Hopefully this shadow isn't too bad. So here's the original design, and this represents one channel. Now remember, this has a dual power supply. So there is one independent power supply for the left channel and one independent power supply for the right channel. So this would represent one channel. So this thing would have, there's actually 2 circuits like this in that amplifier, one for the right, one for the left. So you come out of your bridge rectifier. So here's the secondary of one of the windings for the power, of the power transformer. Center tap goes to ground. Then it goes into a full wave bridge rectifier, and you have your negative voltage and your positive, so your B plus and B minus right here. Those come into these 3 leads. So you see the common, and you have B plus and B minus. And this is just a simple filter circuit. So you have the positive voltage is filtered by this 6800 microfarad, which would be this one here. And the negative voltage is filtered by this 6800 microfarad capacitor, which is here. Very simple circuit. There's nothing to it. What I did was, notice how tall and big this is. Here is one of the new caps. Big difference in the height, isn't there? Now, I could have taken just a standard 6800 microfarad at 63 volts. And I could have used as just a single cap, and they would be a lot smaller. It would be not much larger than this. It would be a little bigger diameter, but it would be about this size. But what I did was I took 2 4700s and put them in parallel. When you put capacitors in parallel, the capacitance adds up, regardless of what each of them are. So if one of these was 4700 and one was 1000, the total capacitance would be 5700 microfarads, if that makes sense. Now, why would somebody want to do that? Well, first of all, I went a little bit higher on the capacitance. It won't hurt in this instance. This is a great big transformer with great big rectifier. It can handle the surge current of charging the little bit. So this will be a total of 9400 microfarads, plus or minus, because these are 20% tolerance. Most capacitors are, versus 6800. So it is higher, but it's not going to make any difference really in the performance of the amp, hardly. It's just going to give you a little more leeway. But more importantly, by putting these in parallel, what happens is if you measure the ESR of this capacitor and you measure the ESR of the other capacitor, when you put them in parallel, it's like putting those 2 ESRs in parallel. And we know when we put a resistor in parallel with another resistor, it makes the total resistance go down. So by doing this, you're actually making a lower ESR capacitor than if you just put in a single capacitor. Now you might say to yourself, why not buy a low ESR capacitor and use one? Well, it definitely can be done, but the more critical design of a capacitor you get, the more limited you get in the availability of what's out there. Capacitors, very low ESR, high capacitance, high voltage caps are expensive, and they're also not a whole lot of them available. So this is a general available off-the-shelf cap. So we get the advantages of the low ESR, we get higher capacitance, and you have smaller size compared to this. So it's an advantage all the way around, and that's why I chose to do this. Now there are some instances where people will also bypass these with a small film capacitor, and they claim that that might give better high frequency response. I've done that before and tried it. I have yet to really be able to hear a difference, and on an oscilloscope with signal generators and so forth, I have not been able to show an appreciable difference. So yeah, you can do that, but if these are good capacitors to begin with, and then you're paralleling them like this, they're going to work pretty well, and you're not going to have a problem with ESR or anything. Now, I know I'm going to get another question. Whenever you have multiple capacitors, why don't you put a resistor across it, blah, blah, blah. Let me explain that. That's what this little drawing is down here. These capacitors are in parallel. And being in parallel, the voltage from here to here is going to be the same on both. Now, even though they may have slightly different capacitances or they may have slightly different ESRs, they may hold a different charge because of that, but the voltage that they will charge up to will be the same because they have the same voltage applied across them. So they'll have the same potential. So the reason for the resistors is when you have capacitors in series, notice this, compared to parallel, just ignore this half for a minute, you're applying a potential at either end of this series string of caps. If these capacitors are not identical in specs, I mean, even though on paper they are, the tolerances are allow them to be slightly different, it is possible that one capacitor could charge to a different voltage potential than the other, which can cause some problems because then one cap will be charged higher than the other, and it could possibly make it exceed its value. Now, this is a precaution, but in a lot of instances, you really don't have to have these. And I know a lot of people are cringing because I'm saying that, but let's take an example. Let's say this is 500 volts here, and each capacitor is rated at a maximum voltage of 350 volts. Well, combined, that's a maximum of 700 volts, correct? So really, you would have to have an almost 200 volt difference before one of these will be exceeding its maximum rating. I mean, when you have that much leeway, the chances of these being that grossly mismatched that one of them is going to exceed its voltage rating is pretty low. Although, when you put surge voltages, you know, with the ripple voltage, because you're putting a load on it, these can see little spikes. But even at that, the only time I would be concerned about these resistors is if these added up so let's go back to our 500 volt thing. Let's say this is 500 volts, or let's say this is 450 volts, and I use 250 volt caps. So I have a total amount of 500 volts max between the two. I'm putting 450 on there. Now that would be a difference, and now these resistors will make a difference. Now remember, these are always high value resistance. Okay, these resistors are high ohms, and as such, they're only going to balance these capacitors out at DC. Once you start putting a load on them, you know, on and off, and the transformers having to charge them as they're discharging, these resistors become irrelevant. So this is kind of just it's an insurance, you know, when it's sitting at idle, but for things that are going to have dynamic loads on them, this is not the way to go. You really, if you're going to have these, yes, you want to have them in there, but you want to have your capacitors, you know, within the ratings that you're not going to have to worry about that. Does that make sense? I hope it does. But you do not, but the point of this is you do not need resistors for this. Picture this, even though they have a shared common, picture it as two separate power supplies altogether, because that's what it is. And these are in parallel. So there's no chance of them being charged to a different voltage potential and exceeding their rating. So that's why it's not needed in there. Okay, I took the long way around explaining that, but I have to say these things because I'll get 100 comments if I don't. And I'm sure I'll still get comments, but hopefully this will explain at least some of it. Okay, we finished the preamp board, or the phono stage I should say, and I did this one off camera because these wires are very delicate. The board will actually swing out this way a little bit, just enough to get behind there to get the capacitors out and get the components off, get to the back of the board. And you do that by, first you take these two screws out here, and then this whole shaft just pulls straight out. This is just plugged in, this little coupling. Once that's out of the way, you just take the 4 screws off the board, and then you have to undo all of these cable ties and so forth, and then this will swing out so you can get to the back of the board. And I replaced all the caps. That's really all I did. It was kind of touchy, so I just had to have the camera out of the way. So I'm ready to put the bottom of this back on. Everything's pretty much ready to go. I also replaced the capacitors on the tuner board, which was very, very simple. You've seen that before. So we're ready to assemble this and do some testing. And of course check the alignment on the tuner, which, if you recall at the beginning of this video, seemed to be pretty spot on. So I don't think we're going to have to do much in the line of alignment. So let's get the bottom put on. Let's get the faceplate on and the knobs, and let's see where we are. We're all assembled except for the top cover. Everything's working perfectly, and we're going to do a couple of amplifier tests. And we're not just testing this, we're going to test our new oscilloscope, our MDO scope. There's a couple things that I'm finding out about it, and I'll share those with you here in a little bit. One more quick note about these capacitors. We went from 6,800 microfarads to about 10,000 microfarads, which isn't a really big jump, which everything will be fine. I will warn you, even though you can stuff larger capacitors than that in there, it is not going to make any difference in how the amplifier sounds or anything like that. Arguably, it may make a very marginal difference in the dynamic power, but beyond that, at this rate, with this circuit, it's not going to make a huge difference. Why do I mention that? Well, you have to keep in mind, as you increase the size of these capacitors, you're also increasing the amount of inrush current and the length of time that you're going to have that inrush current when you turn the power on. Now that's a big strain both on the transformer as well as the bridge rectifiers in there, and it's also going to draw a big arc on your power switch. So this circuit was designed to work with the capacitance that was in there, so you don't want to increase it a whole lot. A little bit will be okay, but a whole lot, bad thing, because this receiver does not have a soft start circuit. If you have something like, for instance, when we did the 2500, or when we did the Pioneer SX1050, some of the larger, more high-powered amplifiers, they had a soft start circuit that would limit that inrush current when you turned it on, and then it would come out of circuit once the caps were charged. This doesn't have that So you can damage your switch, transformer, or your bridge rectifier just by having repeated inrush current with too large of a capacitor. So that's why I chose that. All right, let's look up at this scope here. I really like this for the price. I do really like this MDO 2204EX in this whole series, but it does show some of the corners that they cut. I don't even know if there were corners cut on this as much as we just, and by the way, there's my reflection high, just as much as it just hasn't been refined. They need to fix, and I've just loaded the latest firmware on here, which I was only one revision of firmware behind, and the new firmware does not correct the problem. So, what am I talking about? I programmed in the math expression so that the math will actually show the wattage that is being dissipated by the 8 ohm dummy load. I'll show you how that works on these. If you hit the math function and you go to advanced math and then you go to edit expression, you can see all the different expressions. These are shaded out now because it only allows you to choose items that will make sense in the math expression. So that's pretty cool. And you can see, first of all, you have to take the RMS value of the voltage of channel 1. So we're going to measure the wattage of channel 1. So you take the RMS voltage of channel 1 and you square it. There is no square function on this, so you can't just pick square. There are trigonometric functions, trigonometry, but it won't let you do a square. And I don't believe it'll do, yeah, it will do square root, but it will not let you square a number. So you have to times the number by itself, and I put that inside parentheses, although I doubt that you would have to. It probably would work even without the being enclosed in the brackets like that. And then divide that by the 8 ohms, and that gives you the wattage. So that's pretty simple. And you can edit this math formula. If you change that 8 to a 4, it'll display the wattage into a 4 ohm load. That's how you do it. And it's nice, you can hit OK, accept, and here's where the first problem happens. You can see just by going in here, it changed the units per division. This is not dynamic. In other words, the units per division of your math do not track with the vertical scale of the channel that it's measuring. Now on the Tektronix scope, if you noticed, if I change the vertical scale, the scaling of the math will change with it. This one doesn't do that. So anytime you change anything, you have to bring this into the range that you want to measure. So for instance, this is looking at 5 milliwatts per division. That's why it's jumping around right now. You're actually just looking at the noise on the scope and coming out of the amplifier. So I can change this, and it's 1-to-1. So 2 would be 2 watts per division. So for instance, if I wanted to look at 20 watts per division, I'd set it to 20. Menu off. So right there, it's now sitting idle. Now if I want to put, I have the amplifier set right now with the signal generator, the volume setting, everything, that this will put out about 50 watts per channel. Now 50 watts per channel should be approximately 20 volts RMS. And this down here is showing the RMS voltage of each channel. So these will go to 20, roughly 20. In which case, now that we have this set properly at 20 per division, it should go 1, 2, and a half. So it should go 20, 40, and a half would be 50 watts. And if we turn it on, in fact, there it is. See it? And it is measuring that 50 watts. We're getting our 20 volts RMS. By the way, the RMS voltage that we're using to calculate the wattage, that's where a lot of people will say RMS watts. it's not a true expression to say that, okay? There is no such thing as watts RMS. Wattage is a measurement of the amount of energy dissipated, okay? So when we're looking in these terms of what we're measuring now, we're looking at the amount of energy being dissipated as heat into the resistive dummy load. And we express that as watts, which is the volts times the amps. But the voltage that we use to measure that, because it's an AC signal, is the root mean squared, or the RMS voltage. RMS is a representation. So if you take the RMS of that sine wave, it's going to give you the equivalent DC level that would equal that amount of voltage. So RMS voltage would be an average that would equal that DC level, if that makes sense. So if I put 20 volts RMS on this sine wave, or I put 20 volts DC, it would dissipate the same amount of energy into that resistive dummy load. All right, so now we know that. So the first thing that I don't like is that you have to change this scale. One thing that I do like, as soon as I turn the signal on, bam, the measurement is instantaneous. Now, I don't know if you remember on some of my previous videos using the Tektronix TDS 3032, but you have to have that power, that signal on for a while before the math will actually display. It takes a lot more averages and it takes a lot longer to calculate. This one calculates very rapidly. The downside is it does that because it does not auto scale. The Tektronix will actually auto scale, so it takes a little longer to display the output. So it's a trade-off. The other thing I noticed about the math on this is it shows you the line, but it will not read out the number that it's sitting at. So if you notice it was sitting at 50 watts, it doesn't tell you that it's 50. You actually have to measure it on the scale. So that's kind of a bummer, whereas if you remember the Tektronix, not only did it show you the visual representation of the wattage, but it also put the actual number that it was sitting at in there. This one does not. That's not the end of the world. The auto scaling is a bit of a hassle because you have to go into math and you have to go to advanced math, you have to go to units per division, and you notice as soon as you do that, it immediately changes the scale on you and you have to set it back up and then hop out. So that's kind of a bummer. The other bigger problem, and this is a serious problem, and I emailed GW Instech about this. When you get everything set up, it takes quite a while, as you can imagine, to type all this stuff in, to type that math expression, to set all the settings, the trigger, everything. So in order to make it more convenient, most, if not all, modern oscilloscopes have a save and recall function. And you can do save setup. And if I hit save setup, it lets you save it onto a file. And you can see I have it saved already, which is nice. I'm going to cancel because I already made it. But you have to you can scroll through and select the letters and you can name it something, you know, specific. But when you save this setup, it does not save every setting in the machine. It only saves the button settings here. It does not save the math expression. So when you go to recall this, when you turn the machine back on, it'll recall all of this here, and it'll recall all of the settings here, but it will not recall your math expression. So you have to fat finger that back in. That sucks. That's a simple little thing they could fix in the firmware, and so hopefully they will. But little by little I'm learning this scope, and you know, for the price, I just don't see how there's anything that can beat it right now. I mean, for the price. I mean, you have a multimeter. Let me back out a little bit. You have a multimeter. You have two channels arbitrary function signal generator that also acts as a tracking generator. You have a spectrum analyzer, not just FFT with the math, but a full-on spectrum analyzer, which is nice. You have a little 5-volt power supply, 2 of them, plus and minus 5 volts you could set up. So it's really an all-in-one test bench, and it works. Every function works. Again, there's the little quirks with the saving things and with the scaling and things, and they have been releasing firmware updates that seems to correct them a little bit at a time. So we'll see as this product evolves how good it is. But anyway, that's enough talk about this. I know you're watching this to see the Marantz receiver, but as I'm working with this scope, I'm kind of documenting some of the things I'm finding. I know you'll see that I did that on a couple videos ago as well. Pretty cool stuff. So let's get back to this. Okay, I have the amplifier adjusted at about 100 watts, almost exactly 100 watts output per channel. And I'm going to turn it on, let it stabilize for a second, and we're going to look at the total harmonic distortion at 100 watts. We're going to do a little bit different test with our distortion this time around. So here's 100 watts. So remember, this amplifier is rated at 94 watts per channel. So we're going to go a little bit over its maximum rated power. And you can see that's not a great number. It's about 0.7% total harmonic distortion. Okay, let's turn it off. I'm now going to adjust the amplifier down to half power, roughly, to around 50 watts per channel. And let's see how that affects our total harmonic distortion. I'll be right back. Okay, we're now at 50 watts per channel, and you can see the THD has gone down almost, well, it's gone down a bit. So we're about 0.5 to 0.6% THD. And you have to understand, this meter right now is set to look out to the 5th harmonic. So it'll look at, it averages the first 5 harmonics for the total harmonic distortion. If you use less of the harmonics, you can kind of cheat this number and make it look better. But this is a real world thing, in my opinion, a little bit more real world anyway. So that's 50 watts. We are now looking at 20 watts per channel, and our THD is around 0.1%, so it's getting better. But I'm really not liking what I'm seeing here so far. So we may have to look into this a little more. Let's go down a little more. And here's 10 watts per channel. So you can see that THD, obviously there must be some kind of a harmonic or something that we're picking up that's adding to this distortion, because the distortion is linearly going up, you know, with power. Usually the distortion will stay pretty steady until you get close to the maximum power of the amplifier, and then it'll just avalanche. But in this particular amplifier, we're not seeing that. So this is something we're going to have to look into. Maybe that's the way this amplifier works, but I highly doubt it. All right, we're back to our 10 watts, and you can see where our THD is. But I have the FFT set up on here. I'm not using the spectrum analyzer yet. And you can see, if I can get this stupid camera to pay attention. Now, I have this set on a linear scale. Setting up the FFT on this is not the same as other scopes. Some of the setups are a little different. But you can see, here's your fundamental. And unfortunately, I can't move this right now. But you can see your harmonics. I mean, they're small. Don't get me wrong. I have it set to linear instead of a logarithmic scale. So it's over-exaggerating, but you can see even at 10 watts, and if I go down in power, you can see those stay in there, and then they finally fade away as the power goes down. And if I go up, you can see how crazy they start, and this is where this is coming from, and look at that. And that's at 0.5% THD. So, and of course I'm off scale here, there, but you can see that it's just not real happy. And you can see if I put more of the waveform in there, it gets a little more accurate. So part of this is the meter, or is the scope, the software of the scope. Part of it is we're up to a 0.5% THD, and you can see all the little harmonics that are in there. And again, it's not as much as you think because of the scaling, but still not good. Okay, looking at the trusty old HP 3580A, you can see a little bit better what's going on. Disregard this noise here at the beginning, but here's your fundamental and here's your harmonics. That's still pretty significant. And we're only looking at about 10 watts per channel. And if I go up, I have to change my scaling a little bit. Okay, here we go. And you can see as I go up in power, you see how many, you can just see how many harmonics it goes out. So there's something weird going on with this amplifier, and we're going to have to figure it out. Okay, the first thing we did was just made sure that we went by the book and we set the bias to be 30 millivolts. And you can see we're pretty close on both channels. And we also went through and verified DC offset once again to be 0 volts, and it was 0.2 millivolts, something like that on both channels. It was staying within plus or minus 1 millivolt on both channels. We had it. So everything is properly calibrated, yet we still have this really strange distortion. And we're getting quite a bit of harmonic distortion on this. So if we go up to just a few watts, this is our fundamental right here. Again, disregard this. We're on 2 kilohertz per division right now. So if you look here, that's 1 kilohertz fundamental. There is absolutely no distortion. See that? If we continue up with our volume, we're now at 10 watts. And you can see at 10 watts, you just start seeing the harmonics showing up. And if we go up to 50 watts, there's some significant distortion there. So again, the THD meter and the spectrum analyzer and our MDO kind of all agree with one another. There is some kind of a problem in this amplifier. It shouldn't be like that. At least I don't believe it should be. So both channels, well, let's switch over to the other channel and see what it's doing. Okay, we're now looking at the right channel. We were looking at the left channel, and I'm at a little over 50 watts, and you can see we still have a little bit of harmonic distortion here. It's very low, but it's still there. It's not as bad as the other channel. And if I crank this up, we're now up to almost 100 watts per channel, and you can see it's just now starting to come in there. So the channels definitely are tracking differently to one another a little bit. Again, some of this stuff can be difficult to measure if you don't have this type of test equipment, but the reason I'm doing this is because when I listened to this receiver, it just didn't sound right. It sounded like something was going on. And I don't have the greatest ear on earth, as I've claimed many times, but even I was able to hear a little bit of it. It didn't sound as pure as most of these receivers sound when they're set up correctly. So there's something definitely going on in here, and we're going to have to find it. Okay, I've now changed the sensitivity of the spectrum analyzer, and I'm using a ×1, just a straight through probe, and if you can see, I'm connected right down here in the amplifier at the input of the power amplifier. So we're looking at the output of the line stage, so where your volume and tone controls and everything are. So let's try that now. Let's turn this up. And I'm going to go back up to that 50 watt range. All right, let it settle. Has to do one more sweep. And you can see our distortion is there. Now the preamp should never give you this kind of distortion. This should be, you know, a pure looking signal. And obviously it is not. It is anything but that. You can see all the distortion. So really your power amplifier is just amplifying what it's seeing there. I'll now move the probe over to the other channel, and I have a feeling we may see something similar to that. And here's the other channel, and we're seeing that same distortion on it as well. If you notice, the first harmonic here is bigger, and then they tail off a lot faster than the other channel. So I'm convinced right now that our power amplifier is just fine. Let me turn the volume down. So our power amplifier is just fine. Where our problem is in the preamp, and now we have to figure out why. Could it be something to do with the power supply? It has to be something common to both channels. In other words, both channels are exhibiting this problem. Chances of both of them having the same issue are pretty low unless we introduced it in there. Now, I was very meticulous about replacing the exact type of capacitors. The only thing we worked on here was the caps, if you remember. I did not change any of the values. I even kept the same voltages of capacitors. So I highly doubt that we introduced that in there, but there's always a possibility. Maybe I got something wrong. The other thing that could be that's common to both, though, is the power supply. And of course, we measured voltages on the power supplies a little bit to make sure they were there, but we really didn't look very carefully. So we're going to, next thing in our troubleshooting, very carefully, we're going to look at the actual power supplies. Okay, looking at our modified schematic that I'm holding in front of you here, these two little pink dots that I put here show the negative and positive 20 volt supplies, and that whole line stage is operating off of plus and minus 20 volts. So we really need to get onto this J809 and J810 and see if there is any kind of problem with our voltages there. So let me get on 809 and 810 and I'll be right back. Let me put my mic back on. Alright, so we're on J810, which is right here, and that should be our negative 20 volts. And I'm looking, and we have negative 20 volts, and at least as far as ripple is concerned, it's very small. But it's 19.1, so it's a little bit low, but that doesn't really concern me because a lot of these supplies are like that. And if we move over to the 810, or 809, I'm sorry, there's our positive 20, and you can see it is 19.2. So we absolutely have our plus and minus 20 volts. So it's not a power problem. And it doesn't appear that there is any ripple on there, although we could use an oscilloscope to verify that more, but I really don't think that's an issue. And if I turn the volume up, I'm just looking at these power supplies, they are rock solid. Nothing is moving. You can see right over here it's not changing. So, and if I move over to this one, which is the negative 19, and again I crank the volume, it drops about 1/10 of a volt, but we really don't get any kind of ripple as per se. So yeah, I don't see that as being a real issue there. So we're going to have to go a little bit further now. Okay, we're going to use a little bit of an unconventional way to troubleshoot this. Some of these voltages on these differential inputs to the preamp and tone amp circuit are not right in line with where they should be. They're off a little bit. Of course, our minus 20 volts is our minus 19.2 or whatever, and that's good. But the rest of these voltages are just ever so slightly off all the way around. For instance, the negative 17.4 is only negative 16 point something on both sides, and so forth. Now, the first thing I want to see is, do we have a clean signal coming into the amplifier or into this board? So this is the input coupling or input decoupling capacitor, or coupling capacitor, however you want to look at it. And this is a 1 microfarad 50 volt. I put a film capacitor in here. It was originally a low leakage electrolytic. We're going to check right here. This is 0 volts here. You certainly don't want to put a DC level on the spectrum analyzer, but I am going to use the spectrum analyzer to investigate the distortion coming into this circuit. It should be very, very low, almost non-existent. Now, I can't measure here without using a decoupling capacitor, but we can measure it here. So that's what I'm going to do, and those 2 points are right, I'll zoom you in, right here and here. These are the 2 capacitors, and they're coming in from your balance, or I'm sorry, from your volume pot. So that's coming straight in. So all I'm going to do is I'm going to look here, and I'm going to look here, and we're going to turn the volume up again in the same manner where we were getting that strange harmonic distortion before. And we're just going to see if our distortion is present. So here we go. Come on. I hate adjusting the camera. Here we go. All right. So we're on the first channel now. I'm going to turn this up. And again, we're putting a relatively high signal in there. Now let's let it settle. And you can see our fundamental, and there's absolutely almost nothing in there. Those tiny little bumps are completely inaudible. And you can see as I hold this on there and it settles, there's basically nothing there. And if I move over to the other channel, same thing. There's no appreciable distortion there at all. You can see. So I'm fairly confident that we're not getting any distortion at all at the input. Okay, I'm at the output of the differential amplifier and its little transistor on the other end of it. And you can see it's amplified that just the tiniest little amount, but really, considering this thing's sitting open and everything, that is still not, and I'm moving over to the other channel here, that's still not much in the line of distortion. If you look, I'm looking at the ratio between the fundamental and the harmonics. It's not the same as what's coming out. So I still don't believe that's where our problem is. Where I was looking was right here and right here. These are the outputs of this little input section. So from here it goes into our tone control. Now our tone control, right now we're in bypass. So all of this is being bypassed and it's going directly into this second amplifier here, you see. So we're going to now look over here at this other set of capacitors, and then we're going to look and see what's going on with these guys. You know, I have to admit, although this might turn out to be a difficult thing to troubleshoot and figure out, I am actually refreshed by the fact that there's something new here that we can troubleshoot that's not just, you know, replacing a capacitor and finding a noisy transistor. This is the kind of stuff that is interesting to me. So now it's a challenge. I don't believe that there should be this much distortion in this circuit. Now, common sense might tell you that when you measure both channels, they're two separate but identical circuits. And when you compare them, they are both performing in a very similar manner, although one does seem to have a little bit more of the harmonics than the other. We can see that. So we do know that the circuit is influencing the signal. We also know that where it comes in, now we probably need to look at the signal path a little more carefully on the big schematic, you know, the main wiring diagram, to see. I'm pretty sure that other than going through some switching, the signal comes directly in from the input jacks through some switching and directly into that volume pot. So that kind of tells me that, and we did see where it's coming out of the volume pot, the signal seems to be relatively clean. There's no distortion really there. But we're going to do a couple preliminary tests before we pull this board, but then I'm going to pull this board and we're going to start really looking at things. I may even try totally removing the board and perhaps, let's see, perhaps we'll even power it up from an external power supply with our plus and minus 20 volts and just see how it performs on its own. It's a lot of work to pull the board, but hey, I'm doing this at this point in time because it's a challenge. Okay, when you don't know where to start, you start at the beginning. So here is the input coming from the signal generator. We want to see what our baseline is. How does the signal look that is going into this amplifier? And if we look up here, I'm driving the signal in there right now, and you can see there is the fundamental. There is absolutely nothing, no distortion whatsoever, none. If I shut the signal generator off, you can see the fundamental goes away. Disregard this noise spike here, and we have a perfectly silent signal. Turn the signal back on, and there's our fundamental. Nothing. Totally clean. So we know that we have a nice clean signal going into the amplifier. Okay, we're going to move the camera around an awful lot on this for our troubleshooting, but I'm going to let you follow me along here what I'm doing, or follow along with me with what I'm doing here. Here's our auxiliary input, and we just verified here that we have a totally clean signal. It comes out of here, it goes into the P400 board. Now the P400 board is your phono stage, and it's your input select. It will come out of that board and it will go into the PS01, which is the board that has all those push button switches. And it comes in, where does it come in at? Comes into to these jacks here, and then it exits the board after going through the switching and goes into this JE04 and JE05. So you can see onto PE01, which is where our pot is connected. This is the preamp, or the tone control board we were checking. So we're going to go up here and we're going to look at JS44 and JS46. You see, those are the inputs to the volume pot. All right. So right now I am on JS46, and you can see that right there, JS46 on this board. I have the tone control board pulled. And I have the amplifier unplugged. There's no power. This is all passive until it gets into this board. And if we look up here, we have our fundamental signal. I hope you can see that. And a really, really clean signal. And if we move over to pin 46, or I'm sorry, I was on 46. Here's 44, which is the other channel. And we look up here. Again, we have a very, very clean signal. All right. Okay. So we have a good signal going up to the volume pot. Now what we're going to do is we're going to move over to the output of the volume pot, which happens to be the input of this board, which happens to be pins JE06 and JE07, which are these two here that go into those capacitors we were looking at, remember? So we're going to move this around. Let me get the camera out of the way for a second till I can get onto these connectors, and then I'll be right back. Okay, now I'm looking, instead of at the input of the pot, we're looking at the wiper of the pot. So the input's here, the wiper is here, this is the loudness tap, and this is the low side of the pot that's connected to ground. So I'm on the pin on the board that goes to this little capacitor down here, which is the input of the tone control board, and it comes off of this pin right here, so you can see, and then that is wire wrapped up to here. Now, with the volume all the way down, we should have no signal. And of course, we have no signal. Again, disregard this little noise spike. That's something, that's because that's before the 0 point on the spectrum analyzer. So you'll see that little thing in there. And let's reset this a little bit. It doesn't really matter for this range, but we'll get it over here close. Okay. All right. I will now turn the volume pot all the way up. So it's up to maximum now. And look at that. How about that? So there is something in that circuit on that tone control board that is causing distortion. Obviously, it has to be some sort of either inductive or capacitive reactance that's causing these harmonics. I don't know. The amplifier is unplugged. There's no power. And all we're doing is we're going through the switching from the input jack, the auxiliary input jack, into that pass-through on that push-button board, and then over to this the volume pot. And the volume pot, when it's turned all the way down, we have nothing. When it's turned part of the way up, there's your fundamental, and there's no distortion that you could see. And if I keep going up, you don't see anything yet. And right about at maximum, you really start to see it. If I go down just a little bit, I mean 2 clicks, 3 clicks, now it starts to taper off. 4 clicks from maximum, and it's gone. So there is a little bit of distortion when this pot is turned the whole way up. So it begs the question, does it have something to do with this new potentiometer that I put in? I don't know yet. We're still going to look. But we do know that the problem is somewhere around this board, because we don't see it at the input, but we do see it at the wiper end of the pot, which is connected to that capacitor. So the next thing I want to do is I'm going to remove those 2 little coupling capacitors. So if you look down here, we're going to take these 2 caps out, and we're going to just leave this where it is. So we're going to isolate the rest of the board from the potentiometer. So if we look back at our schematic, here's the capacitor, here's the pin over here, here's the pin going to the wiper of the pot. These are connected to ground. This is all ground. And this is the high side of the pot, and that's going to the output of the switching network. So by removing those two input capacitors, we're isolating everything after the potentiometer. Okay, I've removed the capacitor. Here's the empty connector for this channel. And we're going to turn the volume pot all the way to maximum. Our spectrum analyzer is still connected to the same pin. And if we go up here, absolutely no distortion at all. So there is something on the other side of this capacitor that is causing that distortion to happen. Now, is it our capacitor that we're using? I don't know. But it is definitely something in there that it's not happy with. Okay, I'm now on the other channel, and I still have the capacitor in there, and you can see we still have a little bit of garbage there. So let's take, while this thing is hooked up like this, let me get in here and remove this capacitor. If I can reach it. Here we go. Okay. All right, cap is removed. And look at that. Noise is gone. So we definitely have a problem with something on either the capacitors themselves or something connected to those capacitors. So now that's what we have to look at. Well, I think we're going to have to think about this one for a minute. If you notice, there are capacitors back in the board. I have the volume turned all the way up. And take a look. There is absolutely no noise whatsoever. It's perfectly clean. Now, what did I do? Well, as you can see, the film capacitors have been removed. I took them out. I've used these countless amplifiers I've used these in, and they've always been superior, especially in the audio path. These are those WEMA, these are the Chemet capacitors. I use these in the WEMAs. They're both very good film capacitors. But I actually replaced them with a set of electrolytic Nichicon fine gold. And you can see right there that little gold capacitor that's out of focus. Let's back out a little bit. See it? There it is right there. That one. It's a standard audio grade electrolytic capacitor. Now, I'm not convinced that this fixed it. I'm going to put the board back in and we're going to test it again. And we're going to test the output where it goes up into the amplifier module, because I still have a really hard time believing that that's what was causing it, but you saw it with your own eyes just like I did. So let's put everything back together. Okay, we are now looking at the input of the amplifier board, and we're running just between 50 and 60 watts per channel, and you can see it's back. Not as bad, but it's there, and you can see it changes a little bit. Each time it sweeps through, you can see that these peaks will change a little bit. See that? So we still have a problem, but I think it's a little bit better. So we have to still go in and look more at this board, and this is where I think we're probably going to need to pull this board to really check it. How do you like this janky looking setup? So you can see I have my plus and minus power supply connected, and I'm powering this board up, and I have the internal power supply removed. And I've set the power supply to the 19.2 volts that it was, that we're getting out of this. And if we look down here, I found a couple things that are interesting. First of all, yes, we're still getting the distortion, and of course you can see it on the waveform here. It's pretty bad. See the top of that? This bottom isn't too bad. The top of this is pretty bad. And if I go over to the other channel, it's even worse. Not only do you have a problem here, but look at this. The bottom of this is misshapen as well. However, let's go back over here. Back to the other channel that's a little bit better. And you can see this is proper, but we still have this noise, distortion up here. Watch what happens now. All clear. All I did was I moved it from 19.2 volts up to 20 volts. So that's how critical that voltage is. Now, that being said, I can reduce the input. I'm putting 650 millivolts RMS into this circuit right now. I'm not sure what the input sensitivity is supposed to be, but that cleans that right up. However, if we go over to the other channel, looks better, looks pretty good. Now, here's the other thing I noticed. The outputs on here, let me get you all in frame here. The output is JE09 and JE10, and you can see I have them marked here. JE09, you can see this 4.7 microfarad capacitor, and JE10, we have the other 4.7 microfarad capacitor. And looking at the schematic, you can see here they are. Here's this one, and down here, here's this one. Those are your outputs. And if you notice, the positive should be facing the collector of the transistor. It's a negative voltage there. See how they have that? However, when I look at this one here, you can see the negative lead of the capacitor is very clearly connected to this pin, to the output, like it's supposed to be. But when I look at this pin down here, the capacitor is backwards. And when you look at the actual screen print on the board, it is showing, you can see the little plus symbol down there. See it? See the little plus? So it's marked wrong. Now, I do capacitors one at a time. I pull them out and I kind of hold them in the position they're in, and I put the new one in the same way. I'm pretty sure that's how this one came out, but not 100%. It is possible I could have flipped this around. Now, some people will actually mark the capacitor that's, when it faces the front of the board, they'll take a little Sharpie or put a little dot. I never do that. I have never really had this problem. It's hard to really tell, but regardless, this capacitor needs reversed. I still don't think that's going to 100% fix everything, but I know that that is going to affect it. So let me flip this cap around where it belongs, and I'll be back. Okay, capacitor is in the right way, and I have the spectrum analyzer, and you can see there's just the teeniest little bit, but it is way improved. And I have the voltage set directly at 20 volts, and I'm putting 650 millivolts in there. Let's move over to the other channel. If I can get it connected there, okay. And let's see what we get. And that one is just absolutely dead silent. You can see, you almost can't even see anything there. Okay, we're getting better. So that backwards capacitor was absolutely causing us some problems. But it's still not everything, because this channel is still a little bit quieter than the other. Okay, that channel is good. And if I move over to this one, and you're seeing just some noise because I'm not getting clipped on here real good. Wait till it sweeps and resets. And you can see, look at that. So one channel is still getting a lot of noise on it. So we're going to have to figure out why. I don't know if that's the one with our reversed capacitor that I switched back around. Let's hook up and see. All right. Yeah, that looks to be the one. If I go to this other channel, let's see what it does. It goes away. Yep. So it's still, that channel is still bad. There's still noise on it. All right, I started poking around, and this transistor right here is just, I could see the noisiness in it. I think one of them was noisy. So I replaced all four. So if you look back here, so I replaced this, this, and this. These are those 2SC 1345s, and you can see how tarnished they are. And also I replaced them with KSC 1845s. After doing that, here's the one channel. That looks pretty good. That little blip there is just kind of some noise, I think, from the probe. Here's the other channel. Wait till it sweeps. Dead silent. So we have even more of an improvement. So we're going to go back through now and look at the output again at the input of the amplifier. Okay, here's our amplifier module, and you can see where I'm looking at it, right at the input. And if we look up here, very nice. And let's move over to the other channel. Okay, and look at that. Somewhere between the output of that board and the input of this, I'm still getting noise. So let me unplug the connector here, like that, and it drops. How about that? We still have a little bit, but it's better. Of course, that's because there's no load on that capacitor right now. So we're still not out of the woods yet, but we're getting closer and closer. Well, I think I found the final problem. As you can see, it's gone. These teeny tiny little bumps is all there is, and you have to understand we're looking at a logarithmic scale. So from here to here is a huge amount. You know, it's 20 dB per, or 10 dB per division. So 10, 20, 30, 40, 50, 60, almost 7, it is 70 dB down. So huge difference. And moving over to the other side. Wait till it sweeps, and you can see it is also very good. So what was it? What was the final problem? Well, let's go down to the schematics. And yes, it is a messy bench. A messy bench is a happy bench. All right. So there wasn't much left because we had a good signal here after we replaced that transistor and flipped the capacitor around and replaced those front end caps. This was good, finally, on both channels. But still, over here, we were getting, one side had noise, the other side did not. And if you notice here, your preamp out and main amp in, these are those terrible switched RCA jacks. So when you plug an RCA connector into there, it unconnects this little switch here, or disconnects this little switch. So this is, I think this had some tarnish in it. I jumpered it out basically from here to here. The problem went away. Then I kind of jiggled the connectors around, and you can see where I am over here. Yeah, I'm using all kinds of technical terms today, huh? And from jumpering from here to this yellow wire, that's what cleaned it up. And then taking it off, I took a pair of pliers and just kind of moved some things around. Kind of went like this, and it cleaned right up. So it tells me that we need to clean these contacts a little better in here. And I think that's going to be all. It's going to be working. Okay, I think I have everything in shot here. I have the dummy load connected. I have the signal generator connected. I have the spectrum analyzer connected to the output once again, so we can monitor the output to the speakers, or to the dummy load in this case. And let's go and do our 10 watts again. That's actually above 10 watts. Right there's about 10 watts. And we can see very, very clean now. The distortion is gone. And if we go up, there's still almost nothing. Just the first harmonic, or second harmonic, is just very tiny there. And that's about railing the system out. And you can see third harmonic, we got a little bit, but again, this is a logarithmic scale. That's very, very low distortion. You can see as the amp warms up, it gets a little bit higher, which is okay. But we're actually running that at the, it's a 94 watt amplifier. We were running it at almost 100 watts. So, long story short, it looks like the problem is gone. Okay, I've now swapped left and right channels around so that we're monitoring the other channel. Same thing, look, almost nothing. I bet you that we're going to get really good distortion figures now. So let's move over to our distortion meter. and see what we get. Okay, there is 102 watts per channel. And if I go down to about 65 watts per channel, look at that. That's what we want to see. I think we have it where we want it now. Okay, let's look at our square wave and see what that looks like. And it looks relatively square. I'm not going to rail it out too hard on that, but as you can see, the square wave looked really good. We don't have any kind of ringing or anything like that. So let's do a frequency sweep. Okay, here's our frequency sweep. And you can see it's a little bit bass heavy. And then at 20 kilohertz, you can see it just kind of shrinks a wee little bit. And I've noticed on these Marantz amplifiers that they do have a little bit of low end. At 10 hertz, really low frequency, you can see where it's just a little bit higher gain than in the 20 kilohertz, but it's pretty flat. It's not too bad. And of course I had to change the record length and so forth because it was getting too noisy. But I think it's okay. And again, I don't have the tone control on. It's on, you know, no tone control. If we turn the tone control on, you can see it stays pretty flat. So I'm happy. Okay, just to verify our frequency out a little further, there's 40 kilohertz, 50 kilohertz, 60, 70, 80. So we're at 80 kilohertz, and you can see it's not down a whole heck of a lot. So I'm thinking our frequency response is just fine. Okay, just a quick test through the lapel microphone and see what it does. I think it's working pretty good now. It sounds so much better. Even to my bad ears, it just sounds way, way better. So what did we do? That's what we need to find out now, right? Because I'm sure some of you are quite confused about what we did and what caused all this. Well, full disclosure, I think the number one contributing factor to the most problem was that preamp in, main amp in, preamp out jack in the back needing cleaned. That definitely had an effect, at least on the one channel, but not on both channels. The one channel was okay, the other one was bad. So we had an issue there for sure, and we saw that. The one thing that I absolutely could not explain to this moment, I have no explanation, is when I removed these little film capacitors that have always worked fabulous everywhere I've used them, and I replaced them with those electrolytic Nichicon fine golds. And as you noticed, the distortion reduced a little bit by that. You could see it. I mean, you can see we isolated the signal and proved that it was there, that those capacitors made a difference. Now, you have to understand, we weren't looking at a distortion meter at that time. We were looking at an audio spectrum analyzer. And that audio spectrum analyzer is extremely sensitive to the tiniest little amounts of harmonics. So it was showing things that may have been very difficult to hear for some of us, but it was there nonetheless. Now, we also had a couple of these small signal transistors, and they were being used on the tone amp board. But anyway, those were one of them was a little bit noisy. So we replaced that, and that improved the sound even more. We also found one of the 4.7 microfarad capacitors, namely, let's see here, I think it was one of these. It was either this one or this one, was in backwards. And the board is marked backwards, so the plus and minus. That, again, could have been my fault. I may have removed the cap and didn't properly mark it or notate the direction. And using the silk screen on the board, I put it in the wrong way. Or it could have been in the wrong way, and I removed it and replaced it as is and just put it in the wrong way again. We may never know, but just so you understand, it was backwards. So between replacing these 4 transistors, swapping these out with those Nichicon fine golds, reversing this one backwards capacitor, and cleaning those contacts on the preamp in, or preamp out, main amp in, which is right here, you can see the idea is when you plug the RCA jacks into these, it's supposed to break that connection between the preamp and the main amp so that you can run the preamp out to another power amplifier or an equalizer or something else. Or you can take an external preamp and connect it into here and just use the amplifier. Anyway, those little contacts were dirty on one side, and we cleaned them. There you have it. So this was going to be a shorter video, just kind of doing the test that we finally did at the end. And I fully expected it to pass with flying colors like it normally does, but hey, we ran into some problems and got to do a little troubleshooting. So I'm convinced that this amp is at the top of its game right now. It sounds fantastic. The tuner in it is perfect. I did finish checking the alignment. It didn't need aligned. I didn't touch it. So this thing's ready to go out. It's done. Thank you for coming along with me here. I had a lot of fun, and I hope you did too. And until next time, I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again real soon with another project on the bench. Till then, take care. Bye-bye.